Hey, Steffen, what are we looking at?
That's a direct attached copper cable with QSFP28 connectors.
Help me understand, please, what that means.
Maybe a pretty short 100 gig network cable.
100 gig? That's a lot.
Yeah, actually that's 148,809,524 packets per second at a minimum size in both directions.
Cool, and that's what we have in the cloud, right?
It depends. I would say, let's look a bit at Amazon's general purpose M instance family, the 7th generation with their custom Graviton processor. And that one column gives you, for the smaller instance types, up to 12.5 gigs, and for the biggest full server size, 30 gigabits per second. If you need more networking throughput, as I assume you need, you could use the compute optimized, which are in general a bit more higher limits, but especially the network enhanced ones with the letter N in the end. They give you way more, and even like 200 gigabit per second on an instance, so you get 2 of those beautiful cables. Just for your orientation, 100 gig you get for around $1,500 per month, whereas the 15 gigabit instance of the general purpose is around $1,000 a month.
Okay, this 15 is more interesting for me. The others were these up to.
Let's talk about that later, yeah.
Okay. So do we get these 15s, really?
You mean if we really get 15 gigabit when there's a 15 gigabit in the spec? Okay, let me explain. So AWS limits the network bandwidth based on, well, the gigabit per second, in this case, 15. And no matter how big your packets are, the default MTU is 9,100 bytes. With those jumbo frames, yes, you will be always capped at 15 gigabit in this example. But there's actually a second limit, which is the packet per second rate. And this rate is not documented, but calculated to be just enough that with 1,500 byte packets, you can get those 15 gigabits. So for this instance, as an example, it's 1.25 million packets per second. Logical consequence, as you see in the diagram, if your packets are smaller, your throughput in gigabits per second is lower, like 500 byte packets. You just get 5 gigabits instead of 15 and so on.
Where are we actually on this picture? I remember we do have smaller packets at emnify, right?
Yeah, with our IoT use case, we have a rather small average packet size of 150 to 200 byte, and then, well, we might get only 1/10 of the specified throughput, actually. And actually, as we're running network functions, so meaning every packet enters an instance and we forward it again, we have to touch it twice. So usually we would have like 2 network interface cards in good old setups. But yeah, in AWS, effectively, we can think of, we get only 750 megabit through such a 15 gigabit instance bidirectional.
Have you already explained this to finance?
Luckily, I didn't have to explain this yet.
All right, so let me tell you already upfront that we do like AWS. We use a bunch of managed services of AWS. We leverage from the infrastructure that can be scaled horizontally as well as vertically. But we went through quite some challenges during the last years that helped us understand also where limits hit us, why they hit us, and how to overcome them. Therefore, we are here today to give you this knowledge as well and help you take it home. And thanks a lot for our colleagues who helped us throughout this journey. And thanks a lot for the AWS account team as well as the network specialists whom we work closely together whenever necessary. And why are these limits important? So limits are there to protect us from the neighbors. But the neighbors are protected from us as well. So we have to understand where these limits are and when they can potentially hit us.
To give you some context, what emnify does and why those limits are important to us, emnify provides cellular IoT connectivity for IoT devices. So our customers' e-scooters or EV charging stations or whatever they have as their business, they are equipped with an emnify SIM card and then can get to the internet and so on. Using our global IoT SIM card, those devices can then get online pretty much across the world. For lower latency, our mobile core network is currently deployed in 7 breakout regions across the globe, and we offer IoT-specific security features because, for example, an e-scooter probably shouldn't talk to like anything in the internet, right? While we have sales team in the US, the engineering teams are based in the EU and remote, partially if that's relevant for any one of you. So to explain you a little bit better why those limits are relevant, digging a bit deeper into the architecture. So our IoT device is owned by the customer. Actually, I don't even know what I've drawn here. It looks like it has wheels, but it doesn't matter to us. Like, that's our customer's responsibility. Similar to their backend application, which receives the sensor data or sends the commands to the device, their responsibility. But somehow, of course, Internet of Things, right? There must be the internet somewhere in between to relay all the traffic. And how does such a device get access to the internet? Well, it's with the help of the emnify SIM card, which is then the key to access hundreds of mobile network operators. Those network operators are our roaming partners, meaning we have a contract with them, and they relay not only the authentication that the SIM card facilitates, but also all the data traffic into the emnify platform, which is actually a self-developed and by us operated mobile core network. Well, by the title you might guess where it runs, on AWS.
Right, so the traffic that goes via our network is unpredictable. Imagine scenarios where an IoT devices start to reach a backend, and that backend becomes unavailable. It dies, and then all of a sudden, tens of thousands, hundreds of thousands of these devices in a loop try to reach that destination, which for us means a traffic spike in seconds. Some of our customers had also the great idea to roll out firmware upgrades on all of their devices, of course, simultaneously. What it means is actually that the customer pays for this traffic. We are not supposed to lose it. Therefore, we have to prepare for these spikes, and we have to over-provision so that we can react or we can handle these traffic spikes even if they happen within seconds. Therefore, the EC2 economics very much are important for us, as it's necessary to understand what we get for the money, actually. What are the limits of the EC2 instances? What are the potential bottlenecks, or where they hit us?
So in the beginning, we focused on this 15 gigabit by the specification instance, and there were still those cheaper ones, which we actually mostly used to reduce the blast radius, which had an up to 12.5 gigabits. So let's look a bit at what up to means. Fortunately, the documentation is pretty clear about this. It specifies a baseline bandwidth for the smallest one, 0.5 gigabit per second, and the burst bandwidth. And this bursting capability is based on a credits-based mechanism. So when the instance starts, you have like maximum of credits. Whenever you exceed the baseline bandwidth, so are bursting, the credits are depleting, and if you are below the baseline bandwidth, you are earning new credits. So far, so good. One caveat, it's a best effort basis. So it uses shared resources that might be as well used by other customers running on the same machine. So no guarantee that you can burst that high, or just because you have credits for a certain amount of time. How can we monitor whether the AWS network has limited our network throughput? In 2021, AWS has introduced a couple of metrics which are counters that are always increased when the limits are exceeded. AWS doesn't like the word limit, that's why it's called an allowance, but in fact, it's limiting, of course, your network throughput, and dimensions are bandwidth incoming, bandwidth outgoing, and only one for packet per second. I don't know why only one there, doesn't matter, but those give you an indicator when packets have been queued, at least, for a moment in the Nitro hypervisor's network card. And maybe it was dropped, maybe not. That's what the metrics don't tell us. We at least, by that, get an indication that our packets had to wait for a moment, and then maybe they were sent, maybe not. Where do you get This metrics, as Amazon customer, you would first look into CloudWatch as the default monitoring solution. That's actually not the case here. Those metrics are available via the network interface card driver, ENA, that's the Elastic Network Adapter. And using ETH tool, those counters can be read. Meaning, if you want them in your central monitoring, be that CloudWatch, you would have to roll out the CloudWatch agent on your instances and supply a configuration that it actually reads from the ETH tool output. For us as Prometheus users using Node Exporter, it has an ETH tool collector, which is however disabled by default. So if you want your Node Exporter to make those metrics available, you would have to tune that as well. One comment on your monitoring intervals. Even if you enable enhanced monitoring for your EC2 instances, and by that reduce the monitoring interval from 5 minutes to 1 minute, and you have then 1 minute granularity for your network throughput, you might still see occasional that those allowance exceeded metrics are increasing, even so your network throughput is still rather low, right? But of course, those bursts, which might be just a few seconds, are hidden when you have a monitoring interval of 1 second. So don't be too easily confused when a couple of packets are dropped based on the metrics, but you think your bandwidth is super low, right?
Speaking of bursts, we had a very interesting problem actually, where we saw the when we saw packet drops on a C6IX large instance, although the utilization of this instance was very low. So there was like 15 megabits per second bandwidth used, but the bandwidth out allowance exceeded counter was increasing every 5 minutes.
Every 5 minutes somehow rings a bell. Don't we have a S3 upload every 5 minutes?
Exactly. So I digged a bit deeper, and interestingly, this S3 file upload every 5 minutes uploads a file of 9 megabytes. It's nothing. So however, taking some captures, I analyzed that the upload takes 26 milliseconds, apart from, of course, the tool connecting to AWS and so on. If I extrapolate the data to a per second metric, that's approximately 2.7 gigabits per second, but it's still in the burstable rate of the instance, in theory. So let's open an AWS ticket.
Welcome to AWS Premium Support. My name is Steffen and I'm happy to assist you today in your case. I understood that bandwidth out allowance metering has been increasing on an instance which has only 15 megabit of throughput. Please correct me if I misunderstood your query.
That's correct. It increases every 5 minutes.
I see that the path between your EC2 instance and the S3 service traverses via an internet gateway, which limits the packet size to 1500 byte. Would you consider deploying a VPC endpoint to make use of jumbo frames?
We deployed an endpoint, a VPC endpoint, but the error counter increases even faster. The upload is faster.
Oh, then you might be hitting a packet per second limit through a microburst.
That cannot happen. The packet per second error counter is at 0.
Oh, indeed, I can confirm this via my internal tooling. Would you mind doubling the instance size?
No, that doesn't make sense for this use case.
I was glad to assist you today.
Thank you. So what did we learn from this? That limits are implemented at a much more granular level than per second, actually. They are much closer to microseconds, potentially. That the bandwidth out allowance exceeded counter doesn't necessarily mean dropped packets. It means that packets get unqueued because they cannot be transmitted immediately, they stay in the queue, or get dropped or get transmitted, as Steffen explained. You need to monitor your application behavior. You need to make sure that your application is resilient against packet loss and understand whether it impacts your application and not fully rely on the AWS metric. And bandwidth is a shared resource. That's not a surprise. It's in the AWS documentation. Even if credit is there is no guarantee that it can be used. I would suggest we add some more network interface to this instance.
Yeah, nice try. No matter how many network interfaces you have with your EC2 instance, the limit is, of course, fold the whole instance, and thus adding more interfaces does not help. As we heard, scaling up the instance type would help because you get there usually more bandwidth, not linearly by the CPUs, but you get more. as also in the introduction said, you could use network enhanced ones, which give you quite a lot of more network throughput at also a slightly higher price. However, you can also use a newer instance generation. So from the 6th to the 7th generation, there is a 20 to 25% increase in network throughput at pretty much the same price. So if you are on especially the 6th generation, consider upgrading the type at no cost. With the very latest 8th generation of EC2 instances, there is one new option, which is called EC2 instance bandwidth weighting, where you can reconfigure or reassign 25% of your networking throughput or storage throughput to EBS to like give more capacity to one at, of course, the cost of the other. So if you have network intense workloads, but not disk I/O intense, you could shift that towards networking. And if this talk is not so relevant to you because you have storage intense workloads, you could shift the capacity towards the I/O throughput or storage. As we heard, jumbo frames on AWS can make a difference, and in general, it's good to make use of them. Transit Gateway supports that, Direct Connect also supports it, so if they're not enabled for whatever reason, if you have smaller MTUs, think it through if that might really help. Then the, let's say, confusion about those counters increasing that we saw through microbursts, you can avoid microbursts by essentially smoothening the traffic. For us, the simple option is to reconfigure the AWS CLI, which has a parameter to restrict how much bandwidth the S3 transfers take, which is for us totally fine until at least when it continues until like 5 minutes later when the next file is supposed to be uploaded. For our own application, there's a socket option. You could use TC. You could increase the TX ring size using ETH tools. So a couple of options to, smoothen those spikes.
So another interesting challenge we faced was with the packets per second allowance exceeding counter increasing on an instance which was still below the supported packets per second, actually way below. So I opened another AWS ticket, of course.
Welcome to AWS Premium Support. My name is Steffen, and I'm happy to assist you today in your case. I understand that you observed a packet per second allowance exceeded counter to increase on an instance that is order of magnitudes away from its throughput limit. Please correct me if I misunderstood your query.
You understood it correctly.
Do you maybe have fragmented packets?
Yes, I do, actually. How much can I transmit?
Unfortunately, I can't tell you. The limit is not public.
Thanks. Give me a second. Is it 1,000 packets per second?
Yes, I can confirm this is correct, and I can also share with you that also with bigger instances, you would not get more, except if you buy the whole server, then you get way, way more.
That's nice. Okay, thanks a lot. So why do we have fragmented packets? Imagine the IoT device at the left side, the backend on the right side, and this backend sends some UDP packet to the IoT device. It's all good. It's 1,500 bytes big, but we use tunneling in the telco world, tunneling between the home network packet gateway to the visited network serving gateway. We need to encapsulate these packets, and they get fragmented, of course. Let's understand what happens in AWS with the fragmented packets. So they cannot benefit from the hardware acceleration of the Nitro card. They are processed in CPU, and it's in the documentation of AWS as well that they are considered to be exception. However, what is not documented is that it differs also in the egress, or from the egress to the ingress direction. In the ingress, the Nitro standard rate applies, which is still the slow pass, but at least it increases with the instance size. So with going to very big instances, you could get at least some hundreds of thousands of packets per second. However, in the egress direction, it's capped at 1,024 packets per second, which is a maximum number that does not scale with the instance. You could ask whether it's the same limit as the link local queries. Link local queries like DNS query, for example, instance metadata query, but it's a different bucket, so they don't count against each other. How can we monitor for fragmented packets? First of all, if you have a similar problem as we ran into, that the packets per second allowance exceeded counter keeps increasing at a small rate, however, you see that your utilization is way below the allowance, you can suspect this. You can use TCP dump to match the IP header for the fragmented packets, or ask AWS support. Actually, they apparently have some other metrics that we don't have visibility into. But what we can do with the fragmented packets, so first of all, let's avoid them. They are not supposed to be in your network. Don't fragment them. It's easier to say than do, unfortunately. If you have any similar use case that we have, like VPN, encapsulation, tunneling protocols, then of course the packet size increasing, they might get fragmented. So make sure that the MTU is correctly set on the tunnel interface so that the fragmentation happens on the inner packet and not on the outer packet header. Meaning actually we hide the fragmentation from AWS. Make sure also that your instance is sending back an ICMP error, fragmentation needed, whenever the packet should be fragmented, but it cannot. And that assists the sender with implementing or applying the right pass MTU. You can also configure TCP MSS clamping so that the TCP segment size gets lower and the IP packet fits into the maximum allowed size. We can increase the throughput of the packets of the fragmented packets as well by actually moving the fragmentation to the transit gateway. So in case you utilize or you have a connectivity via the transit gateway, you can avoid the fragmentation on the instance, on the EC2 instance, by configuring jumbo frames and let the transit gateway do the fragmentation for you. There is also a brand new feature from the ANI driver from last week, actually, enable fragment bypass, which lifts up this 1024 packets per second limit and leaves the Nitro CPU do the fragmentation, when that means the standard rate applies from that moment on. Be aware that this Nitro CPU is used for other features as well, so you compete with other features like security group setting up, for example, new connections.
In the second part of the talk, we want to share our experience with a closely related yet slightly different topic, which is contract. What does it do? It keeps track of the state of connections, easily illustrated with a firewall where you have an egress flow, and you, of course, want the returning packets of the returning flow also to find a way into your network, even though there's no firewall rule allowing it. And for this, the firewall needs to maintain some table tracking the state of all the connections, including their TCP state. In Linux, you mostly interact with IP tables, although probably one of my first experiences with Linux. I think I failed, never worked this firewall, but that's how many are maybe used to this connection tracking. What's the great distributed firewall that we have on AWS? It's security groups. And you might remember security groups are stateful, while knuckles are stateless, and this is the state which makes them stateful. By the title of the talk, you might guess there are limits for how big this table can be. And unfortunately, there is no documentation and no specification. Also, when you ask support, there is no official number. So what's the effect of when this table is full and you want to have a new connection to your instance? It might fail until there is space in the table when the next connection comes in. You might also see DNS failures because like egress flows for UDP, they might then not work, and whatever, it's then DNS always. If you then want to log into that instance that somehow shows weird behaviors, you might not be able to log into using SSM Systems Manager, or if you use still SSH, because also those connections might fail depending on how big the pressure on that table is. So where are we experiencing this? We have not only one of those packet gateways as we saw before, but we have, of course, multiple of those instances. and that our customers can directly connect to their IoT devices without any NUT in between, or that the IoT backend can actually connect into the IoT device if that's necessary. We offer different VPN services, OpenVPN, IPsec, or AWS Transit Gateway, which we treat as like VPN for the customers who are on AWS. And you might have heard about like security and malware in IoT. I'm sure our customers don't have that problem, and the good enterprise customers also ensure that they don't get this problem by running port scans across their, of course, large fleet of IoT devices, and they need to run it at a quite high pace. And that exposed so many connections to the VPC where we were routing those flows between our VPN services and our packet gateways. How can we monitor for this? At the same time, when the other counters have been increased, AWS added a contract allowance exceeded counter, and what's newish here, January 2023, is an allowance available metric. So for bandwidth, etc., there's nothing, but here you can query like how much space is left in this table.
That's cool, but can we use this counter actually to finally figure out how much is available?
Exactly. Let's conduct a small story when the limit is not documented, but we have a counter here for the C5 instance or the C5N instance. We see that with double the size, it exactly doubles. And of course, that continues further to the 500x large something as well. The 6th generation, we saw also an increase of 12% compared to the 5th generation, which is then quite nice. But what we saw here is that like this extra money that we put in for the network enhanced instance, this gives us not a single connection more. AWS seems to have realized this in the 7th generation, where the regular instance stayed the same, but the network enhanced one got 33% more capacity. So that's not like the throughput, which was like 3 times more, or 10 times more, a lot. At least we have more connection for more money. That's cool. The very latest instance type, C8, same limit, and the network enhanced one is not available. So we have no monitoring metrics, and of course we had again some challenges with those things where we were looking at it. But first we would have to access it, and because it comes via network interface card driver and not via CloudWatch, the driver version needs to be young enough to support this feature. And the current LTS release of Ubuntu 24.04, even so it came 15 months after the ENA driver version, does today not include this driver version, meaning you don't get it on Ubuntu LTS. We have, in the meantime, or since a longer while, then compiled the driver ourselves, which is, by the way, also the official recommendation in the very first paragraph of the FAQ of the ENI. That's what the driver developers say. But what could go wrong if you just develop your network card driver, right? And in fact, a couple of months back, there was an issue with XTP, which only then happened under high load. So be careful, but if you want those monitoring metrics and you are on Ubuntu or any other older version, you would need to take care of that yourself. The counters exceeded versus the available one have to be interpreted a little bit different. The exceeded counter increases when on this specific interface a connection was rejected. So if you want to know how many connections were rejected on that instance, you would take the sum of them. Whereas the available counter, that gives you on all interfaces the exact same remaining capacity, and you should not multiply that by the 2 or by the 3 interfaces that you have on that instance. So pick one interface or take the average of it.
Are you sure that it's any interface that you can pick? I remember we had some challenges with this as well.
Indeed, we were staring quite a while at graph like this, which in green shows the first interface and in yellow shows the second interface, and the time span is around 4 days. And we saw that the second interface was sometimes updated for not within 12 hours. So we were trying to make sense of it. Is it now a monitoring issue, or is the implementation really different between the primary and the secondary interface? We then in the end filed this as a bug report, and it has been in the meantime fixed. So in the meantime, you get the same counters on all of those interfaces. But well, yeah, we got no monitoring metrics, and then we ran it took us a while to understand and make sense of it. Then, if you know it's about connections, you can get an overview of what connections are routed through your VPC through flow logs. I stop ranting about how complicated it is to enable flow logs for the benefit of finishing within time. What can we do against connection tracking? It's a feature which we can luckily disable. That's easy, right? So by the security groups having an incoming rule, which allows from all IPs to traffic to your port 80, and having an egress rule, which allows traffic to all IP addresses, that's important, it must be all IP addresses, then you can disable connection tracking and can have as many connections as you wish. For network functions, and you can imagine also your NAT instance that you might run, because through the use of the local ephemeral ports, you would have to allow like all incoming, all outgoing for all ports, all IPs.
Don't we sacrifice on security then?
Well, I mean, be careful with that. And in general, we should see security groups as a second layer of defense. But yeah, be careful that you're not exposing your services to your VPC or even into the public internet. It was a fun conversation with our auditor when they requested a Prowler report, and we were waiting like, and because we use DBTK, the interfaces are completely taken away from the Linux kernel, and there was no risk with it. But yeah, be careful with that.
So I remember we also had other challenges, and there is this footnote. Are you sure it's enough to disable?
Yeah, the footnote says just accept automatically tracked. So let's look at the documentation. The first sentence pretty much was I just explained you in like 10 sentences. And then unless it is part of an automatically tracked connection. And it's again a list of things where you just cannot disable it. It's similar to like AWS doesn't call things a limit. This is the list of things where this thing above does not apply. So you can't disable connection tracking when the flow goes via a NAT gateway or an egress-only internet gateway and so on.
And where is the transit gateway? We had the problem with that, I remember.
Yeah, we were indeed, 2 weeks ago when we took that screenshot, quite puzzled if our memories are wrong or if the documentation has been edited. And what do we do in this case? We go back in history to May last year. And indeed, there was still the transit gateway attachment. And it was not only removed from the documentation, but also AWS has confirmed that transit gateway as well as gateway load balancers are no longer subject to automatically tracking those connections, meaning you can disable connection tracking. So, I mean, it's super cool that AWS works on improving those things. There was no news article about this being available in 13 or 300 different regions. Yeah, so we just were made aware that the reason for not having incidents in the past month was maybe this optimization. And while I was going back, I was wondering if we were really that dumb back then and we overlooked this. But in 2022, I believe it was, the documentation looked like this. The beginning was the same, so you can disable connection tracking. And then further down comes the next chapter, which I would say, which is called throttling, which I think I never read. And then comes this list. So the AWS documentation over the years became a lot better. So definitely. And it's worth reading it probably every year once again. If you can't or don't want to disable connection tracking and you have to live with it, then you can scale up the instance type. We saw the table. You can lower the idle timers at least, which wouldn't help for our port scan issue, but the default is 5 days. So if you want that connections where the client went away in the meantime are reclaimed within like an hour or 5 hours of idle time, you can just lower that on the network interface. And last but not least, you could lower the cardinality of the flows, which for us was actually the thing we were anyways working on. And well, we have tunnels on the left side, we have tunnels on the right side. What do? We do tunnels in the middle as well. So Geneve encapsulation was what we were working through our re-architecture, and by that we have control over the cardinality that basically the AWS network sees.
All right, so what did we learn from this journey? that the cloud has limits. The cloud has limits for a good, actually. It's protecting us from the neighbors, but they are protected from us as well. We need to understand where these limits apply, what are those limits, and where they can potentially hit us. The AWS documentation got much better. AWS also enhanced its services secretly, which we appreciate. But we have to make sure that we read those documents much more often, it seems. Monitoring capabilities are also helping us. They are very, very good, but we also sometimes spend an immense amount of time trying to understand and are going down the rabbit hole of trying to fight for single packets, which we learn we cannot rescue every single packet. Sometimes it's still a mystery, unfortunately, what's happening. So it's good, we keep learning. And we have this journey from AWS. If anybody from the audience has a similar journey from other cloud providers, we are happy to learn. Please approach us.
And finally, a few resources. We have, this is my architecture video where within 7 minutes, the younger myself explains the architecture of actually this core architecture that we were talking about today. In case you want to try out our platform, we have SIM cards with us that we give you. And a couple of AWS resources. Most and foremost, the very first one, easy to Nitro networking under the hood, a 400 level talk, which goes really deep by John and the co-speaker. And we're very thankful for John taking the time for the call last week to answer a couple of questions and review a bit the statements that we make here on stage. And by that, lowering the risk that we tell you just things which are plainly wrong. It's our words, but so treat it with care, but we are very thankful for that. And with that, thanks for your attention, and we are happy to take your questions.